I'm actually going to present two papers in the next 15 minutes. The first one is on privately sharing a data set. You can find this on archive titled Smooth K Anonymity or on the website of the workshop. I'm Hossein Esfandiari, and this is a joint work with Alessandro, Wahab, Andres, and Sergey, everyone from Google Research, New York. Okay. The main question that we want to answer in this talk is, can we take a data set, manipulate it so that it becomes, and manipulate it and share it with a third party so that it becomes private, so that the users are not identifiable, right? So this is a very general high-level question, and we want the second data set that we are sharing to look similar to the original data set, right? So why do we want it to look similar? Because we want to just share it with a data set and don't care about the optimization problem or machine learning task that the third party wants to solve on this problem, on this data set, right? We are not taking the data set and making a model on top of it. We're just sharing it with a third party and let the third party do anything, right? So we want some very general, like generic measure to hold for it instead of wanting that, wanting the accuracy of a particular model to be good. So there are two notions of privacy. One is like, there might be more. One is differential privacy. There are many versions of differential privacy, and the other one is anonymity, K anonymity. I'm going to look at these two. Differential privacy is the more popular and more like better measure of privacy, and it's in high level. It says that a user's data shouldn't affect the output by much. I'm going to show you like a formal definition, but this is the high level idea. So if we change one user, the distribution of the output is not going to change. K anonymity says that we want to hide each user in a group of users, right? So if you have one user with some specific specification, we want at least K users to look exactly the same as that user, right? So we are hiding that user in a group of users. So what's the exact definition of differential privacy? We say for like, say this D is a data set. We say M of D is the output of our mechanism on D. So it's what's the private version of D, right? Or the output of our algorithm for D, which is supposed to be private. The probability that this output is in a subset, in a specific subset for any subset, should not change when we change the data set. So if we remove, this is D. If we remove one user, it's going to be D prime, right? In the perfect world, these two are equal. If we output like nothing every time, these two are going to be equal. But we are doing something, we are revealing some information, and we are measuring this change, this information that we are changing with this E to epsilon and maybe some delta here, right? So this is the definition of epsilon delta differential privacy. I'm not going to go too much to theory, but it's just saying that the output is like, when you look at the output, you cannot guess about one specific user, right? If this epsilon is small, it's like 0.1, 0.2, this is a very good measure. If this epsilon is large, it's like, if it's 10, this factor is going to be 1 over 2000. So this probability is changing by a large factor, and it makes this particular definition not very interesting, although there might be some other reasons to yet use that privacy algorithm. Okay. The bad news that we show is that in the worst case, there is no epsilon alpha, there is no meaningful epsilon and alpha, there is no meaningful epsilon delta differential privacy mechanism that keeps the input and outputs look similar, right? So for any constant alpha, any constant epsilon, any constant delta, there is no mechanism that's both epsilon and delta differentially private and keeps the input and output look similar by a factor alpha, right? We use Jacquard similarity for this similarity measure. Jacquard similarity is saying, like, look at how many items you change and divide it by the total number of items. But it actually doesn't matter what similarity measure we are using here. If you use like cosine similarity or Hamming distance, they are going to end up the same, right? So in the worst case, it's not possible to do this with differential privacy. If we make this epsilon to go very large, it becomes like n, then this is possible. This theorem is going to fail, but this is going to be meaningless. This epsilon should be some small constant. This delta is usually sub-constant, but here we are saying that even if this is constant, it's not possible. This task is not possible to do. So for this generic task is not possible to do with differential privacy, I'm going to say a few words about like why this is not possible and then go to the next measure. Okay, a very like popular, easy way to do differential privacy is to look at each user and change the information with some small constant probability, right? So if you're like throwing a coin, change the output, change from head to tail and tail to head with some small probability. This is going to make, this is a very like common way to make a mechanism differentially private, although this is not the only way to do this. It's very easy to see that this technique is going to fail. Why? Think of a social network, right? We are going to remove each edge with some constant probability and add each edge with some constant probability, right? How many edges do we have in a social network? We have like 1 billion users. For each user, we have like 200, so like at most like 1,000 edges, right? So 1,000 times 1 billion is the number of edges that we have. Like, and the number of edges that we don't have is like almost 1 billion times 1 billion, right? So the number of edges that we don't have is much, much more than the number of edges that we have, right? So if we add each edge that we don't have with some small constant probability, we're going to have a very dense graph. Although at the beginning we had a very like shallow graph, right? So this is going to fail. But this doesn't say that any mechanism is going to fail. There are many tasks that we cannot use this randomized response algorithm to make them private, but we can make them private, right? Because there can be some correlation, there can be some correlation between these randomnesses, right? We don't have to deal with each edge independently, right? I'm going to yet say a few words why not any algorithm works, but I'm not going to the proof. It's like a little complicated. I'm just going to say how this is hard. So we need to say for any mechanism, in the worst case, there is some instance that this mechanism is going to fail on that instance, right? We actually say that for any mechanism, there are many instances, like half of the instances that algorithm is going to fail on those instances. But to prove this, like one common way to prove something like this is to find one hard example and say that, okay, you cannot solve that hard example, right? One hard input and say, okay, for this input, you cannot solve this input. And this actually gives us a very good intuition, but this is not something that's possible to do for differential privacy. Why? Because for any data set, you can have a differentially private mechanism that matches that data set to itself, but it's very bad for others, right? This is like, if you, for any data set, if you match everything, any data set to that specific data set, it's going to be differentially private. It's very good for that data set, very bad for everything else, right? So we cannot pick a specific data set to show that any mechanism is going to fail on that data set, but we can look at the distribution of the data sets and say that any mechanism is going to fail with some large probability on those data sets, right? This is some like, it needs some probabilistic analysis. I'm sure I don't have time to go through the proofs. So we move to the other notion, K-anonymity. there are roughly two notions of k-anonymity. The first one is k-anonymity by suppression. In k-anonymity by suppression, say we have a graph, we have a bipartite graph. These are users, these are items or features. Each user has some of the features, right? And we want to have these users such that we want to cluster these users such that each cluster is large enough, larger than k, and the features that these users have are the same in each cluster, right? In k-anonymity by suppression, we can just remove some edges. We cannot add any edge. We can just remove some edges to make this, right? This problem is NP hard. There is some log k approximation algorithm for this in theory, but this is a minimization problem. It means that if the output is not going to keep 1 minus 1 over log k fraction of the edges, right? So if k is like you can only change, if the output is only changing 1 over k fraction of these edges, you have something meaningful in theory. Otherwise, the output can be just empty, right? So unless the output is very similar, unless there exists an optimum solution so that the output is very, very similar to the input, like 99%, this means nothing in theory. I'm emphasizing in theory. The other notion is like k-anonymity without suppression, or what we define as like smooth k-anonymity. In a smooth k-anonymity, again, we want to have these clusters, and we want in each cluster, size of each cluster to be at least k, and in each cluster, everyone look the same. But we can add or remove edges, right? But we cannot just add anything or remove anything that we want. If we have one edge, we want at least half of the users in that cluster have that particular feature. Why? Because one of these features can be like, my name is Hossein Esfandiari, right? And if inside this, everyone has an edge to that, which means that Hossein Esfandiari is in this subset. We don't like something like that. We want these features. If you have some edges and if you have some users being attached to that feature, we want that feature to be somewhat general, global. So that's why we are forcing this second constraint. This is something new that we are saying. This is smooth k-anonymity. We actually show that there is a constant approximation algorithm for this problem. It didn't exist for the previous problem. If the output, there exists an optimum that preserves 75% of the input. So if there is some solution that only changes like 25% of this, then we do have a constant approximation algorithm. The previous work, that was a much harder problem, but there was a log k approximation if almost all of these exist in the optimum. Okay, I'm going to say a few words about the algorithm. What we do is that we take this, we solve some facility location problem, we make up some facility location problem, solve that, and that's going to give us some almost balanced k-median solution. And then we keep merging the small clusters in the k-median solution to make them large. And we can analyze how these mergers are changing our optimum solution. We can implement this using LSH, locality sensitive hashing, and we can scale up to like billions of data points. Okay, I'm just going to talk about this. So this is an end-to-end run. For a learning task, this is the test accuracy. This is K for K anonymity. This is majority label accuracy. If you just report one label for everyone, this is the minimum accuracy that we get. This is the non-private accuracy. So this is the only range that means anything to us, right? This is a randomized response for epsilon equal to 10. 10 is a very large number. So DP is going to be somewhere in this range, right? This green one is a smooth anonymity, our algorithm. This blue one is some like famous previous K anonymity result algorithm. And this orange one is using our algorithm, but with the non-smooth version, right? So the gap between non-smooth and smooth is very large, and we are doing better than this particular famous previous work. Okay, I used a couple of minutes to talk about the other paper. Graph structured crawling models and application. This is a joint work with Mohammad Hossein Bateni, Lin Chen, myself, and Sasan Tawakkol, and we are all from Google Research. Okay. In traditional machine learning, we have some input and some label, and we learn the labels from the input. In active learning, we don't have the labels. We have some input, but we need to like discover some of these labels by maybe crowdsourcing, right? So we don't have the labels, but we can evaluate the labels. For example, by running a test, running an experiment, or asking someone, like, do you see a cat in this picture, right? So this is active learning. In active learning, we want to learn something similar to standard machine learning, but we need to keep asking the labels. And when we ask something, we are paying something for that. So we want to minimize the number of things that we are asking, or we want to maximize our accuracy condition on just asking a certain number of questions. So this is active learning. What we introduce here is that in real world scenarios, many times these labels are changing. For example, if you want to guess if there is an air, well, like what's air pollution of some certain point, this is going to change over time. Or if you're asking, is the weather, is the schedule changing for in this specific business? This is changing over time, right? Or is this website updated? This is going to change over time. Sometimes it's updated, sometimes it's not updated, right? So we are looking at like active learning when the labels are changing over time, and we somehow formalize it using crawling. And we said that, okay, in many cases, there is a graph structure behind this. For example, if you're looking at air pollution, the edges, like streets, neighborhoods near each other, there's an edge between them. If there's air pollution in one street, there's probably air pollution in the next street. Or maybe there are edges between the businesses, like between the restaurants in the same neighborhood. If one of them is changes the hours, the other one will change the hours as well. So there are some graph structure inside there's some graph structures that says if one of them is changed, probably these neighbors are changed as well, right? So I'm just going to skip through what we can do, what we did. We formalized this problem by as a graph structured crawling, and we show that in the worst case there can be some solution. There exists some solution such that it's learnable, but it's not learnable in polynomial time, right? So we have to have some structure. We need to force some stochastic structure to get anything meaningful. Then we model this by latent Bernoulli process, by a latent Bernoulli process model. And we say that, okay, this this model, this is a stochastic model that we enforce, can be solved using some exponential size dynamic programming optimally, but it cannot be yet solved in polynomial time. Like this problem is P-sharp, so under some like famous complexity constraint, this cannot be solved in polynomial time. Yet we can use sampling to solve this dynamic program approximately and do it like efficiently. Then we propose another algorithm based on like reinforcement learning. And this one works like much faster and like beats some good benchmarks. So this is our experiments. We are guessing air pollutions, we are learning air pollutions, and this hitting rate is the rate that like, this is just some measure of accuracy, I don't have the time. So we compare this with EXP3 for bandits, some active covering, some previous work active covering, and reinforcement learning is our algorithm. And for these like air pollution tests that we run, we're beating all of them in terms of hitting rate at least. Okay. Thanks.
Yeah, so in the second talk, you kind of alluded to how the graph structure. I mean, I think the intuitive example that you used, the graph structure can kind of have some correlations to the changing labels. I'm curious if in your experiments you kind of have any investigation as to how that graph structure, there could be many ways to infer this graph structure underlying these businesses or parks or whatever. And so you can imagine that inducing one graph structure, say geographically, might make a lot of sense, for example, park hours, but inducing another graph structure, for example, based on co-owners of a restaurant, which might not be geographically located, could influence, could yield different results. And so I guess what I'm trying to allude at is that the graph structure, or how you define the graph structure here, is highly impactful to the actual end result. So I'm curious if you kind of explored how the method you're considering here is like what the variance is with respect to different types of graph structure or induced graph structure.
Yes, this is a very good question. Like the question, if I say it in other words, is like, how do you construct this graph? And this question matters a lot. Like before constructing this graph, you don't know what to do. We sort of solve the other side of the problem. Here we are talking air pollution. So these experiments, we just look at it like geographically, right? But say if we want to run some like health tests, if we want to test for COVID, then the geographic location matters, but social interactions matters probably much more, right? But there you can define like this, you can again define some graphs. So there's some, these edges can be weighted. There are some small weighted edges between in like one neighborhood, and there are like higher weight edges between those who have interactions. But this graph highly depends on the application. So in each particular application, you need to be able to define this graph, and then you can apply these techniques on that graph. And so it matters a lot, but it's like very problem specific.